Okay, folks, good morning. So let's continue a series of lectures with Dr. Adams, the third class of this.
Okay, good morning, everybody.
Good morning.
Seems like the mic is on. So,
Thanks. Could you please turn off the...
oh, very good.
Thank you.
Yeah, that's better. Okay, so for this third lecture, I'm going to switch gears just a little bit, and I'm going to talk about the effects that clusters have on the formation of planetary systems. And with the information that we gained from this study, we can actually constrain something about the birth environment of our own solar system. So to put this in context, we spent the first two lectures talking about the 4 stages of star formation in probably more detail than you wanted to hear. And what we talked about was how each of the sub-processes are carried out to go from a molecular cloud core to a star disk system. Now, in that picture, we talked about the process as if it were just one star forming at a time, and we ignored the rest of the universe, right? We were just talking about the collapse of one individual star forming event. We did have a brief discussion of binaries, but we did not talk about the greater overall environment in which these star forming events take place. But we know that stars form in clusters, shown in this graph here. And one of the things that we're most interested in, I think, in this context of astrobiology is the formation of planetary systems and the effect of anything on those planetary systems. So planets are down here. So what I want to talk about today is the effects of the cluster environment on planetary systems. And you might ask, well, why am I talking about the effects of clusters on planetary systems as opposed to the effects of clusters on the star formation process? And you kind of already have a hint of that from what we talked about earlier, but the short answer is that there's very little effect of the cluster on the star formation process, but there's a sizable and interesting effect of the cluster environment on the planetary systems. So to hone the questions a little bit more precisely, we want to ask sort of two questions. One, how does the initial cluster environment affect the formation of stars and planets? And by formation of stars and planets, what I really mean is the formation of planets and the sculpting of planetary systems in their early phases. And you'll see why I say that as we carry on. And second, once we understand how cluster environments can affect a solar system, we can look at our own solar system and say, well, we live in a solar system. What effects could the cluster have had on our solar system? And can we use that information to figure out anything at all about the birth cluster of our own solar system? Now, just to remind you, although everybody knows these things, clusters live for 10 to 100 million years. The solar system is 4.6 billion years old. So the cluster that we were born in has long since dispersed, and those stars are now scattered throughout the galaxy. Not completely throughout the galaxy, but somewhere in the galaxy, right? So we can't like go into the sky and say, oh, well, there was a cluster we were born in, because it's long gone because of those timescales, okay? Now, the other timescales we want to keep in mind are these. What we learned in the first two lectures was that the infall collapse timescale, the time it takes for one individual star to form, is about 1/10 of a billion years. It might be 2/10. We learned that the lifetime of a disk is 3 to 10 million years. We also learned yesterday that the time it takes to form giant planets is typically 3 to 10 million years. What I mentioned briefly and what will be relevant for today is that the embedded cluster phase is about 3 to 10 million years. Now, let me be slightly more precise about that. It turns out that all stars form in clusters, but 90% of them form in what we call short-lived embedded clusters, and those clusters live for about 10 million years. About 10% of the stellar population is born in bigger clusters. These are the things that are destined to become the open clusters, like the Pleiades you can see in the sky. And about 10% of the population is born in those larger clusters. They live for 100 or 200 million years, typically. Now, of course, you've heard of globular clusters, and globular clusters live longer than the age of the universe. But only a very, very tiny fraction of the stellar population is born in globular clusters. So I'm going to ignore them today. What I'm mostly concerned with is the rest of the stellar population, okay? And just to finish out my timeline, even though giant planets form in about 10 million years, terrestrial planet formation can take longer, up to 100 million years. In our own solar system, at about the 600 million year mark into our history, there was the late heavy bombardment when many asteroids hit all of the bodies like the moon and Earth and then cleared out. And the open cluster lifetime, as I said, is measured in millions of years, okay? Now, very briefly, clusters come in a whole distribution of sizes. And you can kind of think of them as decades in sizes, anywhere from a cluster of 1 star to a globular cluster with 1 million stars, okay? Now, to 0th order, the distribution of cluster sizes, and by size I don't mean physical radius, I mean membership size n, the number of bodies in it. That distribution is mostly first order power law. It's a power law that goes like 1 over n squared. Okay? Now, if the probability, or if the number of stars in the cluster goes like 1 over n squared, or the distribution of sizes goes like 1 over n squared, the probability of being in a cluster is n times 1 over n squared, because the bigger clusters have more stars in them. So that's a 1 over n distribution for probability. And when you integrate that, you get log n. So the cumulative probability is log n. And what that means, if you don't follow my algebra in the air, is simply that stars are equally distributed in decades. There's the same number of stars that form in clusters from 1 to 10 members, as from 10 to 100 members, as from 100 to 1,000 members. Now, we don't know this distribution precisely. We can measure it carefully in the solar neighborhood, which is what I'm showing you here, and this graph is commensurate with what I just said. We can measure it in external galaxies, but for external galaxies, we can only measure the big clusters. In the solar neighborhood, there are no big clusters, so we can only measure the small clusters, and we're not sure how those two distributions match up. But if they match up the way I said, then there's a simple picture with a nice power law distribution. So, long story short is that when I need to integrate over a cluster size distribution, this is what I will use. There are small uncertainties in that, but they're not going to completely, they won't change too much what we're talking about, okay? So, what are we talking about? Well, what we're doing is we're going to inject, or we're thinking of planetary systems that are born in clusters, and we just want to ask the question, well, what does the cluster environment do? Okay? So what can it do? Well, there's 3 classes of things it can do. One is dynamical. There can be dynamical interactions among cluster members. Solar systems can scatter off of each other. Stars can scatter off of each other. We talked about how in very dense environments, binaries can swap. Stars can swap binary partners and so on. The second thing, which you might not have thought about, is the radiation fields. In the middle of a cluster environment, there's lots of stars close together. That makes the background radiation field much brighter than it would be just in the field of the galaxy. That can also have effects. It can lead to ionization, which affects disk physics and hence planet formation. It can evaporate disks and remove gas from the disks and thereby inhibit planet formation. So the radiation fields can play a role on the formation of planets. And finally, there's particle fluxes, both cosmic rays and radioactive nuclei. Cosmic rays are a very important ionization agent for disks. It sets the chemistry and composition and has a lot to do with the nitty-gritty nuts and bolts of the planet formation process. And different cluster environments can have different cosmic ray fluxes because of environmental effects. Second, and more close to home, quite literally, on Earth where we live, our solar system was enriched in short-lived radioactive species when our solar system was born. The most important ones of these are aluminum-26 and iron-60. This is a long-standing problem. There was actually another paper on this on the preprint server just this morning. And cluster environments can produce these short-lived radioactive species by having supernovae go off in their centers, because these species are produced by supernovae. So supernovae in clusters can enrich solar systems with short-lived radioactive species. And those short-lived radioactive species play a big role in turning the heating and ionization of the disk during the planet formation process. So these are the three classes of effects. And the overriding attitude I'm going to take during this talk is that the cluster environment affects planet formation more than the process of star formation. So in the first lecture, I showed you this map of a cluster still being in the process of forms where about half the stars were actually stars and the other half were still protostars, still embedded in their molecular cloud cores. And what you saw is that those cores were moving at half the sound speed, about 0.1 kilometers per second. And the time it takes for the core to collapse into a star is 1/10 of a million years. If you multiply 1/10 of a million years by 1/10 of a kilometer per second, you get 100th of a parsec. The size of that map I showed you was a parsec. So what that means is that during the time that the collapse is taking place, during the time the star is actually forming, it's moving 1% of the way across this cluster. Point being that if you're only going to move 1% of the way across the cluster, you're not going to run into a whole lot of things. There will be very minimal, in fact zero, dynamical interaction during that time. Moreover, so remember our three things. We had dynamics, radiation, and particles. Well, during that short time, particle fluxes won't get very far. And protostars are embedded in an envelope of dust and gas. They're very optically thick, as we saw. So whatever the background radiation field is doing will also have no effect. Okay? So during the star formation process, the cluster has very little chance of influencing any individual star formation event. Now, you have to be careful what I'm saying by that. The cluster environment, before it formed any cores, did produce the initial conditions for core formation. So the cluster environment does play a role in determining how many condensation centers, how many stars will eventually form, and what the initial conditions are for those. But once that is set up, each subsequent star formation event will happen essentially in isolation, essentially as we talked about in the previous two lectures. But once the star is formed, after only 1/10 of a million years, then it's a ballistic thing, as in it doesn't experience pressure anymore. Instead of moving at 1/10 of a kilometer per second, it has to move at a couple kilometers per second, because that's the virial speed of the cluster. So it will be whizzing around the cluster at that speed, and it won't be doing so for 1/10 of a million years, but rather will be doing it for 10 or 100 million years. So during that latter stage, when the star is a star, and it has a disk around it, and has perhaps planets around it, then it can be affected by its cluster environment, and that's primarily what we're going to be talking about today. Okay? So first up, we want to understand how often these stars that are whizzing around the cluster come near other stars. So what we want to know is the interaction rate. Okay? So I'm going to go over this rather quickly. I had a thesis student, Eva Proskow, who did a whole thesis on this, so I'm going to condense her 5 years worth of work into 2 slides. But what she did is she made a bunch of cluster simulations with different membership sizes, n, and she made a model of them so that they were as much like the embedded cluster sample that the Spitzer telescope was observing in the early 2000s. So we used the same radial size as the observations. We used an initial stellar and gas profile that were consistent with observations. The clusters start with gas and then have the gas ejected. By looking at the Spitzer data, you can see the time scale of that, which is a few million years, and we put that in. We put in the star formation history. You can also measure the age spread of cluster stars, and it's relatively small, but it's not zero. So we put that in, and we see some elements of primordial mass segregation, which I'm not going to talk about much. But there's 2 things that I do want to emphasize to you that are not obvious in setting up these cluster simulations. One is that we already talked about the fact that the kernels, or the cores, are moving subvirially during the formation stage. Then the star forms, and the star will move dynamically. And what that means is that when the star first is introduced into the cluster as a dynamical object, it's not moving at the virial speed. So many previous cluster simulations start with everything moving at the virial speed, but here we started subvirially. And what that has the effect of doing is that it makes all of the stars orbit deeper inside the potential well and makes the overall cluster denser than it would otherwise be. So it actually enhances the interaction rate a little bit, and I'll show you that in a minute. The second thing that is not obvious but is important is that when we're talking about these clusters, we'll often have a relatively small number of clusters, or small number of members, like 300. Okay, so if you have a cluster of 300, and it's going to evolve and orbit around for 10 million years, that's actually not very good statistics. And each time you do such a thing, do such a simulation, you will get a different answer. So you can't just do one simulation of that cluster and figure out what its dynamics are. You have to do it 100 times with effectively equivalent but different initial conditions, and then mine the results of those 100 simulations to figure out what your output parameters are. Now the output parameters we're primarily interested in here are the interaction rate. So I can write the interaction rate, it turns out, in a simple power law form. I'm illustrating that in these 6 sets of simulations. So I have stellar membership size 100, 300, and 1,000. And I'm plotting the number of interactions at a distance b or less as a function of b, where b is this parameter that in this scale goes from 100 AU to several thousand AU. And you see that they're pretty close to power laws. Power laws are straight lines on the log-log plot. So they're pretty nice power laws. Moreover, in each case I have 2 different lines. One line corresponds to starting with virial initial conditions, which I said was not the right thing to do. And the upper line, which is the higher interaction rate, corresponds to starting with subvirial initial conditions, which is the right thing to do. And you see that there's sort of a constant factor of enhancement of interaction rate when you do the subvirial thing. Now, each one of these is not the result of one simulation, but rather 100 simulations. Okay, so after all of this simulation, you can model the interaction rates as the rate at which a star encounters another star at distance b or less is equal to some number times b to some power. Now I've just used 1,000 AU as my fiducial value, and then I can choose the result of each suite of simulations will then be a big gamma and a little gamma. Now, if you had just geometry and no gravitational focusing, little gamma would be 2. Because of gravitational focusing, the gamma values you get are somewhat less than 2 because gravity focuses you. And then we have an overall interaction rate. Now, one of the things that I'd like to emphasize to you students is that when you have a probabilistic problem, and here we have a probability distribution for close encounters. So when you have such a probabilistic distribution, you shouldn't characterize it by a single number because you should use the full distribution. Just like when you learn quantum mechanics, you learn you can't say, well, the electron's here. You have to characterize it with the whole wave function. So here we want to calculate the probability distribution. So the answer to my problem, what is the interaction rate, are these power law distributions. Nonetheless, it's hard to actually think in terms of functions. So after telling you that you shouldn't think in terms of single numbers, I'm now going to give you a single number, okay? So if I take these power law distributions, these encounter rates, and I integrate, or I consider the clusters to live for 10 million years, which is our fiducial time, you can ask, what's the average, typical, closest close approach during that 10 million year time window? And the answer is a couple thousand AU, okay? So that means that if you're in a typical cluster, and you're a typical solar system, and you're whizzing around for the typical lifetime, you, on average, will experience one close encounter at about 1,000 AU, and all your other encounters will be at greater distances than 1,000 AU. So 1,000 AU is typically as good as you get. Now, it's not always as good as you get. It's just the typical expectation value of that number. Okay, so if you just want to kind of think of, well, how close are my closest approaches likely to be, that's the number you can hang your hat on. To do the problem right, you do the full distribution. Renato has a question.
Yeah, it's just, what you mean by subvirial is just the initial velocity of setting up the 10th of kilometers per second.
Yes.
So, and that is that your is that the limit, the minimum limit that binds your upper plot there? Can it be smaller than that? If we reduce that, can it increase your
Oh, you mean
top
if,
level and therefore?
oh, you mean if I started at 0 velocity instead of slow velocity? Well, if I started at 0 velocity instead of slow velocity, these upper curves would move up just a little bit. But because energy goes like velocity squared, if I started at 1/10 of a kilometer per second instead of 1 kilometer per second, I'm starting with 1% of the energy.
Right.
And 1% is not that far from 0, it turns out. So you'll move up a little bit, it won't be huge. Going from virial to the observed subvirial is the biggest jump, right? And it's also the right thing to do. Okay, so far in the story, what we have is we've got a good characterization of the interaction rates. I should remark that my thesis student Eva did these kinds of fits for a whole host of different clusters with different properties and so on. They're not that different from case to case, but if you want to know the differences from case to case, she's done it for you, so you don't have to. Okay. Now, once we know that there are typical encounters with, if you want to hang a single number on it, it's 1,000 a year or so, you can ask, well, who cares? What does that do? Well, one thing that it does, and I don't have a slide for this because this was previous work, is that we know from previous simulations that when you have flybys at a given radius, the disks will be truncated. They will be truncated to about 1/3 of the closest approach distance. That's the canonical result. So if you have a closest close approach of 1,000 AU, the disk will automatically be truncated on average to 300 AU. So disks are truncated to 300 AU by the cluster environment. Now, remember what we talked about yesterday. When we make disks, the typical size you get is solar system size, which is 30 to 100 AU. So if you're truncating at 300 AU and your disks are already only 100 AU, it's not a huge effect. But nonetheless, that's what you get. So what we've learned already is that the disk truncation from these kinds of interactions will be modest. You're not going to have really great big disks. You're also not going to make a lot of planets at 400 AU. Now, dialing forward, you all care now about Planet 9, which is supposed to live at 600 AU. It's pretty damn hard to make Planet 9 at 600 AU. You have to put it there some other way. But we'll get back to that. The other thing that these close encounters can do is they can mess up the planets that you already have. So this is a kind of an interesting problem. I've done it a couple of different ways, and I'll show you some of the results. Suppose I have a planetary system with a star and a planet, or maybe 4 giant planets. And suppose I have a binary, because some fraction of the stars are binary. And the binaries fly by the solar system. You will change the orbits of the planets through this interaction. The problem is that, as you'll see, these simulations are wonderfully chaotic. So you have to do many, many simulations to figure it out. And there's also a huge number of parameters. If you're a solar system, suppose you're just the sun and the earth, and you want to say, if I have the sun and the earth only, what will the environment, this field of other stars, do to me, or do to my solar system? Well, those other field of stars include stars of varying masses, but they're binaries, so we have mass ratios. We have the orbit of the binary, the semi-major axis of the eccentricity, and so on. And then we have the way in which the systems are flying by each other. There's an angle, relative angle, there's a velocity, and there's an impact parameter. And then, for each one of those, you can start with the orbits in different phases. So there's a whole bunch of parameters that you have to do. So what you have to do is do many, 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 many short simulations of these flyby encounters, and then mine the results after the fact for the effects, namely the cross sections. And as I'll say a few times, our group has done millions, many millions of these simulations, so you don't have to. Okay? So you can do them with different solar systems. You can do it with Jupiter only, You can do it with the 4 giant planets, you can do it with Kuiper belt objects, and you can do it in different environments. Cluster environments have a background velocity dispersion of 1 kilometer per second. The field has a background background velocity dispersion of about 40 kilometers per second. And we can do it in each case. So just to show you what might happen, this is a case where the Earth-Sun system is interacting with a binary in the field. So the velocity dispersion was drawn from 40 kilometers per second. This is just one simulation out of the whole ensemble that we did. And you see that this is, of course, a typical one, which means it's the best one I got, because it's got the most interesting orbit. But you see that you have, because of the binarity, this particular binary has a separation that's not that different than the Earth-Sun separation, so that means you can get a resonant encounter. So that means that when the red dwarf pair comes in, it orbits around the sun for 9,000 years before it leaves. And during that time, what happens is the red dwarf comes in, the sun gives the Earth to one member of the red dwarf, who then gives it back to the sun, who then gives it back to the other member of the red dwarf, who then leaves the system with the Earth in actually a habitable orbit. Now, this is just sort of a cool thing where a red dwarf captures the Earth. What's, I think, powerful and interesting, at least to me, is that by doing these simulations and calculating how often they happen, we can calculate the effective cross-section that we have for capturing the Earth, the effective cross-section that we have for ejecting the Earth, and over the time that we have left, we can say how likely is this to happen. So there's a few fun facts that you guys should keep in mind. Our biosphere is great at the moment, but even if we don't kill ourselves through global warming and other things, the sun is going to kill us in about 3 billion years or sooner, because the oceans will boil. Remember, all stars get brighter as they age. The sun will heat up with time. The longest our biosphere has is 3 billion years. So I'm going to use 3 billion years as my fiducial benchmark time. The odds of Earth being scattered out of the solar system during this time are about 1 part in 10 to the 5. The odds of Earth being captured during this time are about 1 part in 3 million. So the odds of the previous slide happening are about 1 part in 3 million over 3 billion years' time. Okay? Now there's another curious fact, since this is astrobiology. If Earth leaves, life continues longer. And the reason is that if Earth stays in its orbit, then in 3 billion years the oceans will boil and basically sterilize the biosphere. And in another few billion years, as we'll see, the sun will eat the Earth and it won't even be here. So that's kind of the end. However, if you eject the Earth, then we have a radiogenic heating source inside the Earth from potassium-40 and uranium and so on. That's about 10 to the 4 times less powerful than the sunlight we get. But if you remove the Earth from the solar system, that's all you get. Now that amount of radioactive heating is enough to keep water liquid if you're deep enough inside the Earth. Now the problem is you have to be 14 kilometers in if you have no insulation from outside. No insolation, not insulation, but sunlight. Okay. Now that means there'll be little pockets of liquid water 14 kilometers deep filled with little bugs. And those will continue to last as long as we have radioactivity. And the longest half-lives are actually longer than the age of the universe, just a little bit. So you can imagine life can continue in the microbial form for 30 billion years if Earth is ejected from the solar system, but it will only last a maximum of about 3 billion years if we stay in the solar system. Now, that sounds great, or not, but the problem is that big life like us can only last on the Earth. We can't live 14 kilometers deep underground. However, since this is astrobiology, let me float the following thought. If you make a planet not where Earth is, but out where Jupiter is, it will automatically have lots of ice on it. Remember, the Galilean satellites have 100-kilometer thick ice sheets. So if you combine those two ideas, you have a big planet like Earth and a big ice sheet like Europa, then the radiogenic heating of the Earth will keep water liquid below an outer ice sheet. And that planet can be anywhere. It doesn't have to be in any particular habitable zone. Every zone is habitable. So the most common liquid water environments with energy are actually not on habitable planets, as we know it. They're actually on ice-covered planets. This is what I call my whales in space theory. And I call it that because you have oceans with energetic things, and it'd be hard for land creatures to develop because there's no land, but any aquatic things could, in principle, develop. And the best you can do is a whale, so whales in space. Just food for thought. Back to our story. When we have these binaries flying by solar systems, what we can do is we can look at what happens to the orbital elements of the planets. So in this case, I've made solar system analogs with a Jupiter, which is a Jupiter mass planet at 5.2 AU, a Saturn, a Uranus, and a Neptune. And by calling these Neptune analogs and Saturn analogs, I mean I'm using the current semi-major axes of these planets and their current masses. But I'm starting them at 0 eccentricity. The actual eccentricities of planets are pretty small, but I'm starting at 0. And then after the encounter, I'm plotting the eccentricity and semi-major axis in the final state. So everything starts here, and then after the encounter, we've got a whole bunch of them, so you get this explosion of orbital elements to larger eccentricity. You see that you change the semi-major axis a little bit, but you change the eccentricity a lot. And this is a common feature. It's easier to change eccentricity than semi-major axis. So we can calculate the probabilities, or equivalently the cross-sections, for each of these to happen. Now, just to illustrate this, I'm going to see if my movie works. I'll show you one of these encounters. So here's a binary coming in, and then it hits the solar system, and then it leaves with a couple planets in tow. And this is actually one of the more dramatic ones. So the two lines here are the binary, and they're spiraling around each other, or orbiting around each other as they came in. The movie is plotted from the rest frame of the sun. So as far as the orbits of the planets are, they're going around so fast that you see just little circles. So let me show you that again. If it will run again. Oops. Oh, it's not going to run again, sorry. Oh, there it is. So you have circles, and then once the planets interact with the stars, they move around. Okay. So again, we've run millions of these. And what you can do is you can calculate the cross-section for any change in orbital elements. So for example, one of the things you might care about is the increase in eccentricity of a planet. So here I have the 4 giant planets, from Neptune on the top to Jupiter on the bottom, and the cross-section for changing the eccentricity is plotted as a function of eccentricity. And this is done for the sun, a host star that's twice the sun, a host star that's half the sun, and so on. So for each of these cases, we have cross-sections. The error bars on these cross-sections are actually due to the incomplete Monte Carlo scattering. So that's a measurement of how well we did the calculation. These are typically of order 8%. But what's interesting is that, remember we talked briefly about self-similarity. If you don't remember that, it's okay, but what this means is that these curves are almost the same shape. So I can collapse them into a single curve. And if I take the cross-section at the end, which is the cross-section to increase the eccentricity to 1 or bigger, that's essentially the cross-section for ejecting the planet. So all of these things can be collapsed to a single formula that gives you the ejection cross-section, which is just some number times 1 power of the 7 major axis and the mass to the minus 1/2. This scaling you would kind of figure out from the depth of the potential well. This might be a little bit mysterious. You would think that a cross-section should go like the area, which would go like the semi-major axis squared, but yet it's linear. So why is that? The answer is, again, gravitational focusing. Because of gravitational focusing, you only get 1 power here. Also, if I collapse all these curves to one curve, this value here has a value in AU squared, which is 1350. plus or minus 160. This plus or minus 160 is not the error bar on the individual determinations, but rather it's a measure of how similar or not similar these curves are. What it means is that all these curves are self-similar, they have the same shape to about 10%. Okay?
So all this discussion refers to a sun on the main sequence, no?
A star on the main sequence, yes.
Yeah.
Yes. So, point being, we have cross sections. Now, we can actually now give our first result. Given that we know the cross sections from all this work, and from the previous work from my student Eva Proskow, we know the interaction rate. If I put those two, and we also know how long clusters live. If I put those three things together, I can tell you how many planetary ejections you expect per cluster. And the answer is like 2. It's a couple. So you expect some planetary ejections through these channels in every cluster, but it's not a catastrophic, life-changing, solar system-changing thing. It's a relatively rare event. So you do get freely floating planets through this effect, but it doesn't mean most of the planets are freely floating. Most of the planets are unaffected by this. So as you'll see over and over again during this talk, the effects of clusters on planetary systems are important enough that we can't ignore them, but they're not important enough that they completely change the story. They're in the sort of in-between realm. So what we have to do is we have to do more work and figure out what the odds of each of these things happening is. Now there's another cool result that I wanted to give you, and that is that we can use the same argument or the same kind of formalism to calculate the cross sections for rock capture. So during solar system formation, there's lots of collisions between asteroids and planets, and in our solar system, this continued for 600 million years, okay? Now, what that means is that every solar system is going to eject a huge number of rocks. And the numbers are enormous. Second, people who have worked on these things have figured out that if you have a bacterium in a rock, if the rock is big enough, the rock will protect the bacteria and let it travel from one solar system to another. The size that you need is usually quoted to be a couple kilograms, which is not that big. Our speaker on Monday said it might be even less. So it's even more, bigger effect than what I'm going to tell you. But if you take the number of kilogram-sized rocks that's ejected from a solar system, the number is enormous. The total mass of them is not so much. It's less than an Earth, right? Which is nothing compared to the solar system. But the number is huge, okay? Now we have the cross sections. They're plotted here as a function of velocity just to make a plot. But if you take the cross sections, the time spent in the cluster, and the number of rocks that are ejected, what it means is that every solar system will share rocks with every other solar system in its birth cluster. It's like going to school or kindergarten where every kid shares germs with every other kid. So our solar system will share its germs with every other solar system in its birth cluster. So here's the deal. We actually have life on our planet, at least we think we are, right? If that life arose while we were still in the cluster, we infected every other solar system in our cluster with our life. As in, rocks that carried those bacteria could be captured, in fact were captured by all the other members of our birth cluster. Now what happens next? I don't know. The chances of it living as opposed to just being there and dying, the chance of it landing on a habitable planet, none of that we know. But what I can tell you is that every solar system will share all its rocks with, or some rocks, with all the other members of the solar system, including us. Now it could have been that our life actually didn't originate here. We could be the result of some infection of the kind I'm talking about. We simply don't know. All I can do is the dynamics and do the rock capture cross-sections and the statistics. So what you should take away from this discussion is the following. Clusters have a relatively moderate effect on their solar systems through scattering, okay? We do change orbits, we do share rocks, but these are not catastrophic changes to the individual star formation paradigm that we talked about so far, okay? So let's go on to the next topic, which is radiation. So let me begin by giving you the outline, the bottom line of the radiation effect, and then I'll fill in some of the detail. So we're going to do this a little bit backwards. So the radiation field of a cluster can be characterized in several ways. We have X-rays, we have EUV, which is extreme ultraviolet, which means ionizing radiation, and we have far ultraviolet, FUV. It turns out, and this is not obvious until you wrangle with it for a while, the FUV radiation is the dominant effect, okay? And the reason is that you might think the harder radiation would be more important, and it is on a photon by photon basis, but there's actually more of the FUV radiation because there's more B stars than O stars, it turns out. I'll show you some distributions later, but what you need to know as a summary is that FUV radiation is the most important radiation field. And then you can ask, well, what does it do? And how strong is it? When we measure the FUV radiation in terms of the interstellar value, that ratio is called G. So if G is 1, the radiation field is the same as the FUV radiation in the background of the galaxy. A cluster, or a star in a cluster, will experience a distribution of FUV radiation fields, but 3,000 is a typical value. In other words, the typical solar system in the typical cluster will experience an FUV radiation field that's 3,000 times the field. 3,000 times what our solar system is currently experiencing. And again, there's a distribution around that, which I'll show you. And then you can ask, well, what does a radiation field of 3,000 do? And the short answer is it will evaporate the disk around a solar-type star in 10 million years. It will evaporate the disk down to 36 AU. That's starting to be important. Remember, the dynamical interactions only truncated our disks at 300 AU. The radiation field is evaporating and thereby truncating the disks at more like 30 AU. And that's starting to matter because the outer edge of our solar system is, wait for it, at Neptune, which is at 30 AU. So this is starting to be interesting, right? Now, in a little more detail, this is the composite distribution of FUV radiation for all the stars forming within 2 kiloparsecs of us today. So to get this, what I had to do was I had to convolve 3 probability distributions. We have the distribution of cluster sizes that we measure in the solar neighborhood. So I sample that. That gives me how big the cluster is. Then for each sample of the stellar membership size, I have to sample the initial mass function. And the reason why I have to do that sampling is that we're talking about clusters of only 1,000 stars or 300 stars or 2,000 stars. You don't fully sample the initial mass function, and only the big stars matter because the big stars produce all the radiation. So each time you sample it, you'll get different stars, different masses, different radiation. So you have to sample and sample and sample. So I have to sample the cluster size distribution, the initial mass function of stars, and then I have to sample the positions of the solar systems within the cluster, because the ones closer to the middle where the big stars are will get more radiation than those on the outside. So if I sample all 3 of those distributions, I get one distribution, which is shown here. The distribution is the solid line. A Gaussian log normal is the dashed line, which is very close. So the central limit theorem works. We're not surprised by that, but the width is given by all the composite widths of those 3 distributions. And here we have 3,000 near the peak. We have 300 on the left side and 30,000 on the right side, which will be ballpark values, okay? So this is the FUV radiation distribution. Now you can ask, well, what does that do? So to address that question, we have to build a photoevaporation model. So we have a star with a disk, and the radiation field comes in, heats up the disk material, and makes it flow out. So let me just briefly outline how this works. You can have flow off the outer, or the top and bottom surface, and off the edge. It turns out that by the time you get far enough out where the evaporation happens, you're at basically 30 AU or 40 AU. The edge is substantial area. And since angular momentum is going round and round this way, the stuff here is sort of halfway out of its potential well. already due to rotation if you're going to fly it out this way. So the long story short tells you that you actually get more radiation off the edge than the top and bottom. And if you have that off the edge, it's almost a spherical flow, except that the whole solid angle is not filled. So you can do a spherical approximation to study the flow. Now the hard part is that the radiation field is coming in and the flow is going out, and what matters is the temperature. But for FUV radiation, different temperatures and different densities give you different chemical composition, and different chemical composition gives you different heating and cooling lines. So you have what's called the photodissociation region problem. And what you have to do is you have to self-consistently solve for thousands and thousands of species and heating and cooling lines. And what you get out of doing that calculation is the temperature as a function of optical depth of the flow and the number density. And once you have that result, you can use that in the fluid equations and solve for the fluid flow off of that. I'm going to skip over the details and just give you the result. Given a radiation field, you can then calculate the time it takes to evaporate a disk down to a certain radius. So if I have the 3000 mark, this is the 3000 radiation field, this is near the peak of the distribution I showed you. It only takes a few million years to evaporate at 60 AU. At 10 million years, we've evaporated down to 30-something AU. But it will take forever to evaporate down to the radius of Jupiter, which is clear down here. So you see that a typical radiation field will truncate a disk at about where our solar system is truncated. Even if you have 10 times higher radiation field, you're only going to truncate the disk or evaporate the disk down to like 15 AU. It's very, very difficult to evaporate a disk down to the point where you can't make Jupiter. It's very easy to evaporate the disk down to the point where it's hard to make Neptune. And of course, if you have a weaker field, ain't nothing happening, okay? So that's just where we are in radiation effect space, okay? Now what about EUV, the ionization radiation? Well, here we're at different units. We can do the same thing and calculate the distribution. The peak value in these units is 10 to the 12 photons per second per centimeter squared. Because of astronomical history, the EUV radiation fields and the FUV radiation fields are traditionally given in these different units. But what you need to know is that this is the distribution of EUV radiation, the analog of the one I described earlier for FUV, and this is the peak value. And then we can make an evaporation model for that, which is actually simpler. And I'll tell you why in a minute. But for the typical value, 10 to the 12, that EUV radiation field will evaporate a disk down to 300 AU in 10 million years' time. So, for the expected radiation fields we get in clusters, we take the peak values. The FUV is powerful enough to evaporate a disk down to 30-something AU. The EUV will only evaporate you down to about 300 AU. So the FUV wins. Now, why is the EUV simpler? Well, EUV radiation has enough energy that it's almost as simple as each photon that comes in will release a proton. So all you have to do is the accounting. Now, it's a little bit more complicated than that, but as rule of thumb, that's all you really need to know to do EUV evaporation. You don't have to do any of this messy heating and cooling that I described, okay?
Sorry, when you mean evaporation, you mean the inner part of the disk or the whole?
Oh, most of this flow is coming from the outer disk edge. So it's the outer part of the disk that's being evaporated in this case.
Yeah,
The outer part.
on the outer.
Yeah, the outer part. So you basically, you have a big disk, and then the outer part is in the shallowest gravitational field. So it's easiest to boil off. So that will leave, and then the next outer layer will leave, and then the next outer layer will leave. What these curves show is the time to make it evaporate from a large distance is much shorter than the time required to evaporate from a shorter distance. So the disk will just shrink with time. So if I look at this curve here, at 2 million years, my disk will be at 60 AU, and then it'll be at 50 AU at about 5 billion years, and it will be at 30 AU at about 10 million years, and if I could expose it for 20 million years, then it would be down to here, and then I could expose it for longer, it would be here. So we just kind of climb up these curves and evaporate the disk away as we go.
Yeah, it's the opposite I ever thought. I thought it was first the inner part and then the
Yeah, now your intuition is right for, there's another thing I wasn't going to talk about, but this is, all of this discussion applies only to evaporation due to external sources. In addition, the star itself also has photons, and that flux is a much more intense nearby. So you also get an inside-out thing like you're talking about from the star itself, which also adds to this, but that's a very interesting problem, but it's not the one that I'm doing here because I'm just doing the environmental effects. Every isolated star will have its own internal effects.
external sources. You mean, I don't know, OB stars and
Yeah.
projecting.
Well, in the cluster we have a distribution of stars. Most of the big ones are in the cluster center, and for these moderate-sized clusters, which are the rule, you tend to have lots of B stars. So to zeroth order, we're talking about B stars. There are occasional O stars, and the bigger clusters have lots of O stars, but most clusters have the radiation dominated by their B stars. And that's just because of the combination of the IMF cluster size distribution and the mass luminosity relationship of stars. Did you have a question?
Yeah, no, because in this case, most of the massive stars will have a short lifetime.
That's correct.
Probably the source of this UV field, EUV field, or FUV field will be very short, no?
Well, the O stars will live for 10 million years, and the B stars will live somewhat longer. So you're correct that we can't go to really, really long time scales because the stars will die. But the clusters themselves disperse, the disks are viscously evolving, and planet formation is done all in 10 million years. So as long as the stars live for 10 million years, I'm good. And even an O star will live for about 10 million years. To ballpark you, if I have a 25 solar mass star, I happen to remember this number, its main sequence lifetime is 7.5 million years. But then it will live as a post-main sequence star for another million years. So even a 25 solar mass star will live for almost 10 million years. Okay? So only the stars bigger than 25 will have short enough lifetimes that I would have to worry about them. But most of the stars are actually not even O stars, they're B stars, so they're going to be quite a bit longer lived. At least long enough I can get away with it. So let's keep going.
Fred?
Oh yeah.
Can I ask a question about an exception? I understand that in general we have B stars, but if you have O stars, like for instance in Orion, will there be a specific case from the same math, this photoevaporating disks in Orion, that we see incredible shapes, like cometary-like?
Oh yes. I mean, when you're very near an O star, you will be completely blasted. The disk will be completely blasted away. Near the O stars in Orion, we see these. They even give them the name proplyds, which is sort of a silly name, but that's what they call them. So that will happen. The way to say that is that those EUV fields are at the tail of this distribution, okay? And at the tail of this distribution, you get a lot of evaporation, just like you're saying. The thing to keep in mind is that the peak of the distribution is very far from the proplyd situation. And you can kind of see that this way. In the solar neighborhood, just within 10 or 1 kiloparsec, less than 10% of all the stars are in the Orion Nebula cluster. And less than 10% of the stars in the cluster are actually in the core of the cluster. So the core of the Orion Nebula cluster is only 1% of the population. And not all of those in the core are actually close enough to be proplyds. So it's kind of like 1% of 1%, or 1/10 of 1/10 of 1/10. So it's kind of like a 1 part in 1,000 effect. And that puts you out on the tail of this distribution. But out on that tail of the distribution, exactly what you said will happen, and it's very cool. Okay? It's just that it's a little bit more rare. We think it's more common because those are the coolest pictures and we see them all over the internet. But the average star doesn't do something quite so dramatic, right? It's just like, you know, LeBron James is on TV a lot more than I am, but he's actually not the most common person. So let's see, where were we? Let me speed up just a little bit. Clearly, if you have smaller mass stars, the gravity is weaker, it's easier to evaporate. Second, if you have evaporation acting in concert with viscous accretion, like I talked about yesterday, then you're draining the disk from the inside due to accretion, and you're evaporating it from the outside due to photoevaporation. That will set an overall lifetime of the disk. And for typical numbers, with typical viscosities for the disk, like we talked about yesterday, and typical evaporations, like we're talking about today, these things cross at about 8 million years, so you get sort of a canonical lifetime of 8 million years. There's a whole distribution around this, but 8 million years of the lifetime is perfectly consistent with the plots that we saw earlier in the week. Finally, we can look at the X-ray flux. The X-ray flux is not important for evaporation. Let me be clear, the X-ray flux from external sources is not important for evaporation. The X-ray flux from internal sources can matter, and it will do what we were talking about earlier of evaporating from the inside out. In the interest of time, I'm not going to talk about this, although X-rays can play an important role in ionization. But what you should take away from this is that the radiation effects are actually more important than the dynamical effects in terms of sculpting solar systems. Both matter, but the radiation matters more. And even though the radiation matters more, it does not completely dominate over the individual formation process. Now let me briefly tell you about particles. So supernovae go off in the middle of clusters, and they produce short-lived radioactive species. Iron-60 and aluminum-26 are the two most important ones. These things, these elements get embedded into rocks, they heat up rocks, they differentiate meteorites, they affect planet formation, and our own solar system has an enhanced value of both aluminum-26 and probably iron over the galactic expectation, okay? So what one can do is one can use the same kinds of statistical arguments that I've been using to date to calculate the distribution of short-lived radioactive species delivered to solar systems. And not surprisingly, you get a distribution. So here's the distribution. This is the number as a function of enrichment. Now the enrichment delivery is measured in, turns out, picosons. That's 10 to the minus 12 suns, just happens to be the right value. So what you need to know is that our solar system has an enrichment of about 100 to 200 picosons. In other words, when our solar system was young, some source, and we can fight about it, whether it was a supernova or something else, some source gave us 100 picosons of extra aluminum-26 above and beyond the galactic average. And we see the daughter products of that in meteorites today, so we know that it was live aluminum-26 when the rocks were incorporated into rocks, which happened to be the first couple million years of solar system history. So we know that. What this plot shows you is that to get 100 picosons, you're way down on the tail. The typical value is more like 1 picoson. So we're enriched at kind of the factor of 100 level, and not surprisingly, the chances of that occurring is about a 2% effect, which means that only about 2% of all solar systems are expected to be enriched in short-lived radioactive species to the degree that we are, or we apparently have been. Did you have a question?
Yes, I was wondering if the level of picosons also is matched by iron-60. Do they agree?
Ah, very good question. Here's the story. It's not a, well, the short answer is they agreed within a factor of 2. Okay? So the story is that Iron-60 has to be produced by stellar nucleosynthesis. Aluminum-26 is easily produced by stellar nucleosynthesis, and there are yields from supernovae, which is what I'm using here. In addition, you can produce aluminum-26 by spallation. If you have high-energy fluxes of protons, they can interact with other nuclei and get you radioactive aluminum-26, okay? In the original, well, one of the alternative models to the supernova picture was that a centrifugally driven wind, a la Franck-Choux, would produce proton radiation and spallation and produce the aluminum-26. And at first he thought we could explain all of the short-lived radioactive species without the need for a supernova. And what he found is that if you produce as much aluminum-26 as you need to explain the solar system through spallation, you get way more of all the other stuff. However, if you produce half of the aluminum-26 by spallation, you can explain the beryllium-9 and other short things, but you can't explain the iron. So the picture that emerges from this is that our solar system was enriched by a supernova which gave us all the iron-60 and half of the aluminum-26, and that the rest of the aluminum-26 and the beryllium-9 and other short things were produced by spallation. Now, that's sort of an uncomfortable to have like two sources. However, it turns out that you can see gamma ray lines of aluminum-26 decay and iron-60 decay all the way across the galaxy, okay? And we know the supernova yields, or we've calculated, and I don't know if you believe the calculations, but Stan Woosley and company have spent a lot of effort calculating the yields of aluminum-26 and iron. Long story short there is that when you look at the gamma ray lines across the galaxy, you get the sort of standing abundance of iron-60 and the standing abundance of aluminum-26 in the galaxy from the different lines. And what you find is that there's too much aluminum-26 by about a factor of 2. Now, you can either interpret that by saying, well, Franck-Choux is right, that spallation is a good source of aluminum-26. Half of the aluminum-26 across the galaxy is produced by spallation, half is produced by supernovae, which matches the iron prediction. The alternate is to say, well, the observations are wrong by a factor of 2, and the other explanation is to say the supernova predictions are wrong by a factor of 2. And we don't really know anything that well or that much better than a factor of 2 in either one of those arenas. So I think all of those actually have to be possible. But the picture that emerges is that you get aluminum-26 and iron from the supernova, and then some more aluminum-26 and beryllium from spallation. You had to ask. But that will actually come up later. So I want you to remember everything I just said in about 10 minutes' time. Okay. So let me conclude the first half of the talk. Clusters have a moderate effect on the solar systems forming within them. And what this means is that the environmental effects we're talking about, they're important enough you can't ignore them, but they're not so important that they completely change the picture. So they're neither dominant nor negligible. What do? Well, closest approaches, if you want to hang a single number on it, happen at 1,000 AU. In other words, solar systems will come near other solar systems where near means 1,000 AU. That will truncate disks down to 300 AU from dynamics. But this will be truncated down to 30 or 40 AU by radiation. The combination of evaporation and accretion will put an upper limit on disk lifetimes of order of 10 million years. Planetary orbits are going to be altered, but only moderately. There will be planet ejections, for example, but only a few per cluster. And we can also figure out what the typical radiation exposure is for solar systems, and it's measured in picosons. Our solar system has a plausible enhancement due to supernovae, but it's either a 2% or maybe if you take the factor of 2 we talked about in account, maybe a 5 or 10% effect. In other words, only 1 in 20 solar systems will be enriched as much as we are. So we're in the top half of the class there, or top 5% of the class. So what I'd like to talk about next, and I think I have 15 minutes. Yeah. There's a question that's on everybody's mind, namely, where did we come from? So we live in a solar system. That means that our solar system was probably formed in one of these clusters that we've been talking about this morning. So the question is, given what we learned about how clusters influence the solar system, can we use the properties of our solar system to work back and figure out what kind of birth cluster we might have been formed in, or at least put constraints on it? So this is kind of like playing CSI solar system, right? We have some clues, we'll see what we can do. Now, turns out our solar system has a lot of properties. We know way too much about our solar system. But I have to like narrow down the problem a bit. So these are the properties of the solar system that I'm going to explain. I'm going to use them to put constraints on what the cluster that we were born in looked like. So the first up is that we were enriched in radioactive species, aluminum-26 and iron-60, as we just talked about. So we want to account for that. Our planetary orbits are not disturbed very much. We saw that clusters can disturb planetary orbits. If you look at our planetary orbits, they're nice and circular. There's some eccentricity, but it's pretty circular. So our solar system was not scattered too much. Now, our solar system has two edges. If you reconstitute this solar nebula by taking all the bodies and putting the gas back in, you get a pretty hard edge at 30 AU beyond Neptune. But there's other stuff beyond Neptune, which is the Kuiper belt. So the surface density goes like this, and then there's a big drop at Neptune, and then it goes out for a while, and then there's another drop at 50 AU at the edge of the Kuiper belt. So we have two edges of the solar system, an edge of the gas disk at 30 AU, and an edge of rocks at 50 AU. And also, we have the dwarf planet Sedna, which has this crazy orbit with a periastron of 70 and an eccentricity of 0.82, which means that it's way out there a lot of the time. You do not naturally form something like that from the planet formation picture that we've been talking about this week. However, the scattering interactions I just talked about can in principle produce sednoids. So what we want to do is we want to say, suppose I demand that our solar system have all 5 of these properties. What demands does that put on our birth cluster? So, in a little bit more detail than we were talking about with Renato, these are the short-lived radioactive species we want to explain. So we have aluminum-26 and iron-60 are the most important in terms of they give us the most heating, the most bang for our buck. Beryllium's not so important, but it's there. We see the daughter products of it. So the deal is that iron-60 has to be produced by a supernova. Beryllium has to be produced by spallation. Aluminum-26 can be produced by both. So the picture that emerges is that if you have a 25 solar mass star, you can explain all of this except for some of the aluminum and all of the beryllium, and then spallation, if you don't require it to produce all of the aluminum, can easily produce the required amount of beryllium. So we think that we were enriched with a 25 solar mass star, as in a 25 solar mass star went supernovae while we were still in the birth cluster. And as I said earlier, the 25 solar mass star has a age, or main sequence lifetime of 7.5 million years. So at least there's a chance we're still in the cluster 7.5 million years in. These guys are rare. So what we want to do is calculate the probability that we lived in a cluster that has a 25 solar mass star. So the probability is actually 1 minus the probability of not having a 25 solar mass star. Can't argue with that. And then I can put in that probability, and I get a probability distribution, which is just a simple formula. Next up, our solar system is very well ordered. The eccentricities of the giant planets are 0.049, 0.057, 0.045, 0.11. The inclination angles are a couple degrees. So our solar system is not jostled by interactions very much. Now, we've done these millions of scattering interactions, so I can give you the cross-section for changing our solar system too much. And by changing our solar system too much, I mean doubling the eccentricities or doubling the spread of inclination angles. Nothing particularly catastrophic would happen if our inclination angles were bigger, but they weren't. They're not. So by using the fact that they're not messed up, we can put a constraint on our dynamical history. So the cross-section for messing up the solar system which means increasing the eccentricities or the inclination angles beyond these values, is 400 AU quantity squared. Now you'll immediately realize that 400 AU is bigger than 30 AU, which means that the effective cross-section for changing the solar system elements beyond what they're changed is much bigger than the geometrical cross-section of the solar system. So the stars don't have to come that close before they'll jostle the orbits beyond recognition. Again, it's not catastrophic if that happened, but it didn't happen, okay? So let's see, I can kind of skip this. And if I just use those first two constraints, I get a probability distribution for having a supernova, which increases with n. The bigger the cluster, the more likely you are to have a 25 solar mass blow up, the better off you are. So if I want a supernova, I'm pushed towards having bigger clusters. But if I want to have solar system survival with the cross-section I just showed, bigger clusters are generally denser and more over longer lived. So if I want to have solar system survival, and by survival I just mean not changing the orbital elements more than they're changed, I'm better off for survival in a smaller cluster. The bigger cluster I make, the more likely I am to be scattered, and the more likely I am to not have our observed orbits. So I have two probability distributions, the probability of having a supernova, the probability of not scattering too much. And they work in opposite directions. The joint probability of having both of them is then the product of those, which is here, which puts you at a cluster size of a couple thousand. More precisely, if you only consider those two constraints, the expectation value of the cluster size is 2,000 plus or minus 1,000, and the a priori probability of this is about 1 in 60. In other words, 1 in 60 solar systems will be enriched at the level that we're enriched, and yet not jostled more than we were not jostled. So that's not a problem. 1 in 60 events happen, about 1 in 60 times it turns out. And it's not particularly rare. If this were 1 part in 100 billion, then there'd be only one such thing per galaxy and you would worry. But 1 in 60 is just not a problem. But we are a little bit special, okay? Now, let us put some more constraints on it and see if that changes. So we have the goddess Sedna, who has been honored with this body called Sedna. Turns out that we don't want a scattering encounter to be too close because we don't want to mess up Neptune, but we actually do want a scattering encounter to produce Sedna. Because the best way to produce Sedna, for all these dynamicists who have tried to produce Sedna, is to have a scattering encounter with the closest approach of about 400 to 800 AU. The closest you can be and not mess up Neptune is about 225 AU. So there's this narrow window where you can have a scattering encounter that's close enough to produce Neptune. It basically lifts it out of the Kuiper belt to this crazy orbit, and far enough away to not mess up the giant planets. Also, we talked about the fact that there's a constraint from radiation. The radiation field basically must have a G value less than 3,000, because if it's a lot bigger than 3,000, you'll evaporate the disk down beyond Neptune, and it will be hard to form the giant planets. So when I put those two constraints on the plot, I now have 4 constraints. And it looks like this. So the first supernova constraint was this one. The constraint that I have a scattering encounter that produces Sedna is this one. Note that they're about the same. The constraint that I survive in the face of scattering and not mess up Neptune and other orbits is this one. The constraint that I don't have too much radiation is about the same. So the addition of these 2 additional constraints does not actually change the picture that much. Now quantitatively, you move this over a little bit and move it down a little bit. So now my expectation value is more like 4,000 plus or minus 2,800 or so. But there is, in fact, a solution. If you have a cluster in this general range, you have a reasonably a priori probability of a few percent of having all of those effects that we need to have happen to actually happen. We get meteoritic enrichment from a supernova. Check. We don't mess up the planetary orbits too much. The radiation field will evaporate the disk down to 30 AU, which is fine. You actually kind of want it to be evaporated down to 30 AU because Neptune is there, but it doesn't have much gas, as we talked about. So evaporating down that far is actually a good thing. Those scattering encounters will not change the planetary orbits, but they will produce Sedna, and they will also make an edge of the remaining Kuiper belt at about 50 AU. So all of these properties can be explained with a cluster in the size range. So that all sounds good. So we have this good story. But it's a little bit more complicated. So let me just give you an introduction to this complication. If you want to have supernova enrichment, you not only need to be in a cluster with a 25 solar mass star, which is what we've taken into account so far, but you also have to be the right distance away. Because if you're too close to the supernova when it goes off, you'll strip the whole solar system apart, and that doesn't do you any good. And if you're too far away from the supernova when it goes off, then you won't get the enrichment that we need, and that doesn't do you no good for explaining it. So the window for explaining it is basically from a tenth of a parsec to about 3 or 4 tenths of a parsec. Now, these clusters typically have a size of about a parsec. They have a centrally condensed density distribution. So the probability of being at any given position is sort of linear with distance. So that means you have a 10, 20, 30% chance of being in the right place. So this is not a killer problem, but it's an additional 10% effect that has to go your way in order to get our solar system. Now, if you think hard about this, there's a whole bunch of other things that have to go your way. I've already marked that the 25 solar mass progenitor of the supernova lives for 7.5 million years. Now, only about 10% of disks live that long. And you want it to be, if you want to be enriched, you want the disks to still be in disk form at this moment. So we need to be kind of 10% lucky in terms of the timing, to get the timing to work. Now, it turns out that ideally, the solar system will actually, if it's spent all its time at 0.2 parsecs away from the O star that blows up, it would get a little bit too much radiation. So you want it to live near the edge of the cluster for most of the time and happen to be at 0.2 parsecs at the moment of explosion. The orbits are radial, and that's not a big effect, but it's another 10% effect that has to go your way. We already talked about the window of scattering encounters. And also, in order to have a good chance of producing Sedna, we want to live in the birth cluster for more like 100 million years. Now, 10% of all stars live in open clusters, or born in things that become open clusters and live in that environment for 100 million years or 200 million years. But yet, that's another 10% effect that has to go your way. Okay? And there's a few other caveats that we can consider. I'll put this slide on the website for you guys. There are some other alternatives to nuclear enrichment. The bottom line is what we talked about before. We need some combination of spallation to produce a beryllium and supernovae to produce iron-60. These other things don't work so well. Now, the last thing I want to talk about is Planet 9. So given these considerations, I only have 3 minutes left. So given these considerations, we can apply them to Planet 9. So if you'll remember, there's this posited new member of our solar system, which we call Planet 9. We have not seen it yet. What we've seen is evidence for it in that it lines up the orbits of Kuiper belt objects. And if it's real, it has an eccentricity in this range, from 0.4 to 0.9, a mass of about 10 Earths, and a semi-major axis of 400 to 1500, and a fairly high inclination. So, given this hypothetical Planet 9, there's 2 questions. One, if the sun was formed in a birth cluster and we had Planet 9, would we retain Planet 9? And second, how the hell did Planet 9 get there? In other words, can you make Planet 9 through these scattering encounters? So let's talk about that. We can do scattering calculations like the kind we did earlier to see whether we can do 3 different things. If you have Planet 9 in an interior circular orbit, can you scatter it into its crazy elongated current orbit? Can you steal Planet 9 from another solar system? Can you steal Planet 9 as a freely floating planet in our birth cluster? So these 3 channels are ways to produce Planet 9, and we have calculated the cross-section for each of these events. Also, if you have Planet 9 in its current orbit, there's a cross-section for ejecting it from the solar system. So, we've calculated the cross-sections. Long story short is that these are the probabilities for ejecting Planet 9. It depends on the eccentricity, and it depends on the environment. So in the birth cluster, the background velocity dispersion is expected to be 1 kilometer per second. These upper curves show the probability of ejecting Planet 9 as a function of its semi-major axis. So we expect so for large semi-major axes, the probability of Planet 9 is over unity. That just means that your chances of keeping it are low, right? Because it's an exponential thing, right? But for a smaller semi-major axis, it's kind of a 50-50 proposition. So if you want to have Planet 9 in the birth cluster, and the solar system lives in the birth cluster for the time we expect it to live in the birth cluster, given everything else I just said, the chances of keeping Planet 9 is about 50%. So we got to be lucky. Not crazy lucky. Flip a coin, half the time you're going to be right. But it's not guaranteed. Once you're out in the field, the velocity of dispersion is much larger, the cross-section is much smaller, and then there's only like a 1% chance of losing Planet 9. So once you're in the field, Planet 9 is relatively safe. So the basic results are scattering into its orbit, capturing from another star, and capturing from a freely floating state are all low probability events at the 1% level. Ejection from the solar system is likely if you're in the birth cluster and unlikely if you're in the field. Now to close, I want to come back briefly to these 2 questions. Remember at the beginning of the talk we asked ourselves 2 questions. 1, how does the cluster environment affect the formation of stars and planets? And 2, what can we say about the birthplace of our own solar system? The answer to the first question is that we have this set of results. We have distributions of closest approaches, we have distributions of radiation fields, we have disk evaporation rates, we have cross-sections for solar system disruption, cross-sections for rock capture, cross-sections for Planet 9 effects, distributions of short-lived radioactive species enrichment, and so on. Each one of these individual distributions is the answer to the question, what does a cluster do? A cluster won't do one thing all the time to every solar system. All you can do is say, well, the distribution of radiation fields it gives you is this. Given that distribution of radiation fields, here's what evaporation you can expect, and so on. So these distributions are the answer to the first question, what does the cluster environment do to you? The answer to the second question is that the birth aggregate of the solar system is probably a moderately large cluster. The numbers we get are about 4,000 plus or minus 2,000 in membership size. If you want to expand that, assuming we don't quite know what we're talking about, it's really this decade in size from 1,000 to 10,000. So our birth cluster probably is in sort of a mid to large, but not too large cluster in this realm, okay? So this is a good place to stop, and I will take questions. So thank you for your attention.